So, welcome everybody to this other Thursdays of seminars here at Brias. It is really my pleasure to introduce our first speaker, who's Denis Dochain from UCL. So, Denis is one of the most well-known control guys here in Belgium, so I'm not going to make the list of everything that he has done and all the many achievements he has done, because otherwise we are spending a lot of time and then I'm reducing the time for which he will speak, and I'm sure he will present a lot of interesting things. So it's really my pleasure to introduce him, and I leave him the stage. Thank you, Denis, for coming.
Thank you very much, Emanuele. Do you hear me without the microphone? Is it okay? No. So I shall use this microphone. My voice is not very loud, so I probably need a microphone.
No, it cannot move a lot. It cannot move a lot because you have recorded.
Oh, so I have to stay here? Is that?
Yeah.
Okay, good. I'll do my best. You know, it's not my temper to remain just fixed on the floor. Anyway, I'll do my best. So please tell me if you believe that I'm not doing it correctly. Should be okay. Yes. So my presentation today is about adaptive control of reaction system. And so maybe I need to tell you about what is a reaction system. So reaction system is any system when you have transformation of matter. So this applies in a number of fields. So biological systems, and indeed this includes also metabolic engineering or synthetic biology, if you prefer. I mean, all these terms tend to evolve in time, but this typically is the way that you look inside the cells. Chemical systems is another type of reaction system. Environmental system, and I use here the example of wastewater treatment, which is one of my favorite type of application. Ecological system, and this include microbial ecology, the fact that you have, let's say, interaction of between different species in biology, and also this include all these, topics related to epidemiology. So the SRR model is nothing but a classical, let's say, ecological model. Indeed, it was one of my surprise. When the, let's say, the COVID crisis came, that so many people, start to work on controlling, epidemiology. But then I was really surprised that most people tend to reinvent the wheel, because all they were touching this was stuff that were known by a lot of people, including me. But anyway, that was great, and so this means that also this is a nice type of application of reaction system in the large sense. And I'd like to mention also plant growth, which was one of my favorite topics. So a plant is clearly a biological system, but not as microbes, but then it's an important biological system, and therefore it is a reaction system. Okay, so what is important to understand, what is different from reaction systems with any other dynamical system that we consider in automatic control? First of all the variables, these are concentration, temperature, quantities in ecology, for instance, these are positive variables, okay? In mechanical engineering, you have, let's say, position or velocity. These can be positive, negative, whatsoever, but this is not the case here. These are all positive. Energy that you have are not quadratic functions. And it's because, in some sense, it's fundamentals of the thermodynamics in this case that related to this kind of reaction system. It's really related to the fact that the properties don't need to come with, let's say, square values of variables to come with energy. Dynamical models, typically dynamical models comes from fundamental, let's say, balances, mass energy balances, and sometimes momentum balances, which is probably also very typical from what we have in reaction systems. On top of that, most of the model, 99% of the model are nonlinear, but also with a large uncertainty on the parameters. And also there's a lack of accessibility to many important variables. in many instances, or for any of the example that I mentioned before, it's very difficult to get, let's say, online, precise measurement, reliable measurements of, let's say, the variables that are important for the dynamics of the system. Okay, so I would like to start with what I call general dynamical model, then move to what I would call two key properties of any reaction system, and then I will deal with state and parameters estimation and then adaptive control. Okay, so what I say is that this equation, which is, say, a matrix equation, is a general way to look at any reaction system in a confined medium. Okay, confined medium means that you have, let's say, the fact that, let's say, the system is homogeneous. But in that case, but you can, let's say, consider, let's say, variation of that, but typically this is always the same. Always the same. The first, let's say, element is the fact it is the transformation of matter. Okay? So typically, Kr of x is the multiplication of matrix, which is in chemical engineering known as a yield coefficient matrix, stoichiometric coefficient matrix, and in bio, or in any other case, it's a yield coefficient matrix. And R of x is a reaction rate, is let's say, the rate at which a transformation takes place. And all the other terms is the fact that the medium is not closed. So if it's closed, you don't have that term. If it's not closed, then you have, let's say, the interaction with the environment. So F is the feed rate, so what you put inside the medium. Minus Q is the term of, let's say, gas that may go off of the medium. And the last term is called typically the dilution rates, but it is the quantity of matter that leaves the medium. Okay, so this is typically transport dynamics. Okay, so lowercase q is typically a volumetric flow rate, and V is the volume. And having said that, I have everything to go ahead. So let me take a first example, anaerobic digestion, which is a wastewater treatment. Well, it's a long wastewater treatment, I mean, known for let's say, centuries. And so it has the advantage to produce methane. So it was very popular at some point, let's say, typically with the first oil crisis in the 70s, because people say, oh, no, we found an option, an alternative to produce energy, let's say, without oil. Anyway, so this is a long story. But then this is process, is a very complex process. You have, in bio, they say this is an open medium. This means that you have a lot of different species, a lot of different bacteria, if you prefer, that interact. And when I say a lot, it can be thousands. Okay, but there's one way to look at simply is that to consider that typically you have only two populations, and so this is what I say in this case a simplified reaction scheme. So I have a first step which is called acidogenesis, so when you transform the organic matter that you want to degrade by acidogenic bacteria into volatile fatty acids. And these volatile fatty acids are then degraded to produce methane and CO2 at the same time, but this is done with methanogenic bacteria. So if I consider that, my model will be written as follows. I have mass balances for, let's say, the acidogenesis, so the first two elements in my first reaction, and then the second step, when I have look at, for instance, which is interesting is to see here, this is volatile fatty acids. It is produced by the first reaction, consumed by the second. Okay. So this is very simple. This is mass balances, very, very, very easy to note. So okay. So in this case, I use the notation, classical notation of bio, which I say that I have D, which is the dilution rate, which is nothing but the ratio of Q over V. And so if I want to put that in my general dynamical model, it's very simple. I just have to define typically my, let's say, state vector here with all the components in the reactions, and I have to define my yield coefficient or my stoichiometric coefficient matrix. Okay, So for instance, if I look, so each column corresponds to each reaction, and each row corresponds to let's just say the intervention of one component in each reaction. For instance, if I look at this one, volatile fatty acid is produced by the first one, is plus K3, and is consumed by the second, is minus K2. Very simple. And it's completely general. So what is interesting in that case is that for bio, if we have bacteria typically the reaction rate is the product of what is called the specific growth rates and the concentration of the bacteria involved in the mechanism. So this is known as an autocatalyst. Okay, so you need the biomass to have the reaction, but the biomass at the same time is produced by the reaction. So that's why it is not just a catalyst, which is quite known by chemical engineers, but it's an autocatalyst. Okay. Okay. Anyway, this is a word that you could keep in mind if you wish. But of course, let's say the issue in that case is that what can I put in mu? Is mu just a parameter? No, it has to depend on the system variable. And for instance, you know that you don't have anything to eat, you will not grow. This is exactly what this curve shows. The more I eat, the more I grow. And this is known as the mono model in that case. But then you can have indigestion. Okay, you eat too much, you get sick. And this is this term. So this function is monotonic, and this one is non-monotonic. And so when you reach some maximum at some point, then you have decrease. So the fact that you have decrease of the growth by that time. Okay, and then you can have a lot of other dependencies. For instance, you know that one type of microorganism will be active in a specific range of temperature. Okay, fine. So let me look. So I look at the bio. So let me look at the chemical example. So in that case, typically, what is a matter of, let's say, issue for control is the fact that you have a reaction that can explode, if you wish, okay? And this is typically known as non-isothermal exothermic reaction. So when let's say the reaction enthalpy might be negative in that case, and so then this can be a source of problem when you want to control it. So typically, what is different between the example that I've shown before is not let's say the energy takes place, okay? And so the energy balance can be expressed in terms of temperature, which is a variable which is rather easy to measure, okay? So in that case, I can rewrite my model also in my general dynamical model by considering that T is one process component. Okay, let me move to a third example. It's a ecology example, the famous prey-predator model, okay, where you have, let's say, a mass balance for the prey, when you have a growth rate and a constant term by the predator, and for the predator, that's the production by consuming the prey, and then you have a mortality rate, okay? Okay, this is this is exactly what I would have in that case in the general dynamical model. Once again, it fits in the general dynamical model. Okay, and this is a great, example. I could tell you for long about that model because there's so many nice properties, and the fact that it's periodic. You know that. If you are a little bit aware of that, with that model, it was the idea that it was able to emphasize the fact that typically when you have a lot of prey, then it tends to let's say, move to an increase of the predator. They have a lot to eat, but then the number of prey decreases, and then the predator don't have to eat anymore, so they decrease, and at the same time it's a kind of a periodic, let's say, a behavior, which is observed, let's say, a lot in nature. Okay, so now I have my basis, I have my model, and I can start working, okay? But I want to do more, because I want to see what can I do? Can I take advantage of the fact that this reaction system, they have some specificities? And so that's what I would like to mention, is that reaction invariance and slow fast dynamics. So the notion of reaction invariant is very well known by chemical engineering in general, and chemists also at the same time. It's the fact that when you have a reaction A given B, this means that the number of moles of B that I produce are exactly connected to the number of A that I consumed. Okay, that's a constraint. So in mathematical sense, this means that there is a mathematical constraint somewhere. So typically when you have a system which is closed with no exchange with the environment, in that case, this is a true mathematical invariance. Okay, this is exactly what I show here. So there's a general properties. So I can make a state partition XA, XB, such that the sum matrix Ka related to XA is full rank. And then the property is general. The property is that I can define a variable Z, which is a linear combination of XA and XB, where A0 is the solution of this matrix equation, in that case. And then in that case, I can rewrite the dynamics for XA and Z, and it is completely equivalent. So these terms are only related, so independent of the kinetics, or the transformation, let's say. And in that case, you know, these terms, which are typically transport dynamic only, if the system is closed, this must be equal to 0. That's what I said just before. This is exactly the fact that in that case, it is a mathematical invariant. Okay, and this is a very strong property. And so the idea, I mean, can we use that for control? Second property is what I like to call slow fast dynamics, often mentioned as singular perturbation, but I like the way this slow fast dynamics. And so it ends up to come up with a very well-known approximation in chemical engineering, which is called the quasi-steady state approximation. So let me try to explain how I can come up with that. Assume that I have a sequence of reaction, A1 given A2 given A3. And I assume that the first one is slow and the last one is fast. And these are the reaction rate related to each reaction, okay? And I assume that at least, so K01, K02 are kinetic constants, but they have to be such that the reaction rate must be equal to 0 if there is no reactant, okay? If I have no A1, I cannot have the reaction A1 given A2, okay? That's simply that, and that's why I put this here, okay? Okay, and so intuitively, I mean, if you are engineers and even if you're not a chemical engineer, you will understand that very easily. If this reaction is slow and this one is fast, this means that any time that I produce 1 mole of A2, it is directly transformed into A3. So it's like having one reaction, A1 giving A3, okay? And so, okay, so how can I come up with that conclusion? So I define a small parameter, which is the inverse of the kinetic constant KO2. And I rewrite my dynamical mass balance for A2, so the concentration of A2, pre-multiplied by epsilon. And so I put epsilon to 0, and then I obtain this algebraic equation. And since typically I assume that this, generally speaking, this term phi has to be different from 0, the only option is that the concentration of A2 is equal to 0. Okay? Second step, I make let's say, the mass balance for the sum of A2 and A3. I come up with this equation, but since, so this becomes the mass balance equation for CA3 because CA2 is equal to 0. And so this is done, because typically I say that A3 is produced by the first reaction. Okay? Simply as that. Fine, so I can come up, let's say, with a general rule with respect to that. But then what is interesting is that, for instance, if you look at metabolic engineering, this property is very largely used too. Okay, it's a very common, let's say, assumption that it's used. The quasi-steady state approximation that I justify here is very common in metabolic engineering. So I try to make the connection with every field that I mentioned before. Okay, let's move to state observer. And then I would like to say I can use my reaction invariant. My reaction invariant says that I can write the dynamics of the system, part of the dynamics, independently of the kinetics, which is an issue because I mentioned that I have a number of models, let's say typically for the reaction rate, but all these models, they are typically, let's say, heuristic. There's no fundamental model, let's say, used in practice for kinetic model. So in that case, so this is an issue. I would like to have a state observer which is in some way insensitive to the knowledge of the kinetic modeling. Okay, and so now I make another partition when I put x into x1 what I measure and x2 what I do not measure. I rewrite my z that I mentioned before as a linear combination of x1 and x2, okay? And I have to make sure that I can invert A2 in that case. And so in some cases, it's just a left inverse, but it's a classical inverse in most cases. And so then what I do, I compute z from the equation that I mentioned just before, and then I invert this relation just to get, let's say, an estimate of the variable that I do not measure. And this is an observer, even if I don't have, as a classical observer, if I don't have correction term, this is an observer. Because I can guarantee, that's why we call it an asymptotic observer, we can guarantee the convergence. And the guarantee of convergence is related to this condition, which is very classical in adaptive control, which is called the persistence of excitation condition. So I can guarantee that as long as the dilution term, let's say the flow rate, if you prefer, is not equal to 0 for too long, then I'm pretty sure that the estimation of the x2 at will converge to x2. Okay, so the estimation of my unknown state will converge to the true value. Okay, application. So ETBE, so ethyl tertiobutyl ether, is an additive or unadditive fuel. So this is the case when we have what we call a fixed bed reactor in that case. And so the reaction is typically transformation of ethanol and isobutene ETBE. Its non-isothermal is exothermic because it's minus 40. The process, so I mentioned it. So what we measure is the temperature at 4 locations. Okay, these are the 4 locations. So inlet, outlet, and 2 positions in the reactor. And also measure, let's say, the concentration via an HPLC at the output of the reactor. So these are typically the measurement that we have in that case, the temperatures typically, and let's say typically the concentration in that case. And so this is typically what we obtain in terms of estimation. So as you can see, I have a quite good fit, let's say, of the different variables in that case. Okay, online parameter estimation. So as I mentioned that there might be a lot of uncertainty typically on the parameters in the model, so probably need tools to, let's say, be able to reconstruct, let's say, the parameter online. And so I go back to my general dynamical model. I assume that, let's say, the reaction rate are partially known. Okay, so this is the unknown part, this is the known part. Okay, and I rewrite my dynamical model as follows. So if I do that, and I assume that I have a number of measured or observed component which is equal to the dimension of the matrix H, which is here. Okay. And so I just use, let's say, classical observer-based estimator, so with this correction term related to the states in that case. And so classical parameter design, omega, gamma. I know that typically I have this kind of rules. I can do that, it works. But we found one way which is much better than that, which is very easy. So we say we can use a transformation, an auto transformation in that case, when I have zeta, which is the inverse of the submatrix K, U, multiplied by the state vector, okay? And then, so if I use that, this is how I can rewrite the equation, but it happens that in that case, because of that, because of this transformation, if I do that, I can rewrite my, let's say, observer on a basis of 2 by 2 equations. So one estimation is related to one measurement, or more precisely, one combination of measurements. Okay, and then in that case, it's very easy to calibrate, because I have only a system of order 2, which is very easy to calibrate. This is exactly what we have in that case. So we found a way to get very simple way to calibrate the system, and a calibration that can be different for each parameter that you want to follow. Because in that case, typically what you have to follow is not constant parameter, but parameter that might change with time. Okay, so that's why I would like to illustrate that in the next slide. So application now is animal cell culture, so which is also very well used in pharmaceutical, let's say, applications. So in that case, we have, let's say, reactions came with 2 reactions. Glucose is in both cases. In one case, you only grow biomass, let's say, it's called respiration, because you have oxygen, okay? And then in the second case, you produce lactate, okay? And that's interesting. So this is different from what I did before. We have a fed batch reactor. What is a fed batch reactor? In a fed batch reactor, let's say, you fill partially the tank, and then you introduce matter progressively until the tank is full. Okay, so that's why it calls fed. So the first phase is fed. I'm feeding it, and then when it's full, then I wait for the reaction to be completed. So this is what is called batch. So what is called fed batch, and that's very interesting, because you don't have steady state in that case. There's no steady state. The steady state is at the end, and when there's nothing to be consumed anymore. So this is a kind of system that which always in dynamical situation, which is very different from what we have in many cases in other automatic control application. So we measure glucose and lactate plus some offline measurement of biomass, and we like to estimate the 2 specific growth rates. So that's very interesting. So the measurements are at the top, okay? These are the 2 mu that I would like to estimate. So if you look at the 2 mu, the 2 specific growth rate, they have a completely different behavior, okay? So that's what we need, some tools to calibrate differently, so we can make that independently. This is great. And what we did, the challenge was to make sure that we could fit. So the circle here are the offline data. Okay, I use at some point some asymptotic observer. This is the red line, and the green line is the validation. What is the validation? This is a crazy exercise. In that case, so is a completely unstable system. So you try to compute the mass balance equation for the biomass in that case, but just putting the value of the estimation of u on the 2 mu's. And if you look at these equations, the equations are unstable. So if you make a slight difference in the calibration parameters, the estimation explodes. So this is really a very interesting exercise in that, and very important in that case. Okay. So if you want to interested in by that type of let's say kind of results, this is the result that I obtained a few years ago with Romeo Ortega and co-workers. Let's say on extending, let's say, the result that I mentioned just before. Let's move to adaptive control. So. And so typically adaptive linearizing control in that case, the fact that the model is typically nonlinear, so we have to find some way to handle the nonlinearity, and at the same time, since there's a lot of uncertainty, it might be good to make sure that we can adapt the controller to the let's say the changing behavior of the system. So typically, if I want to write it in a general way, I can write the dynamics of the output that I want to control that way. And so this is typically done by using my slow, fast, let's say, dynamic reduction, okay? And typically, I need to have all these terms. So I typically need to have a reaction term somewhere. If I have gas, that's important because it's easy to measure, so it's probably important to have it in my equation. And then I need also the fact that I feed, let's say, the system by some let's say reactant or external, let's say external feed. Okay, so very simple way. I want to have, so this is a first order let's say differential equation. I say I want to have first order dynamics in that case. Oops, I combine the two, and I typically have my control, let's say, equation. If I decide that the flow rate is my input in that case, which is really standard, let's say, in any case in reaction system. And so since I have, let's say, uncertainties on the parameter, I typically have to estimate alpha, beta, and gamma, and the reaction rate, which might be a sort of uncertainty too. Okay? So let me show you a simple example. I go back to my anaerobic digestion example that I've shown at the beginning. And so in that case, I mentioned volatile fatty acids, and if you are not chemical engineering, this is something that you don't know what it is, and I don't ask you to know what it is. What you have to understand in this kind of systems, volatile fatty acids is a source of instability. So typically, at some point, what you may have is what they call accumulation of volatile fatty acids. And so when you have a lot of volatile fatty acids, they tend to inhibit the growth of the methanogenic bacteria. Remember that I show you what I call the indigestion model, aldane model, which is a non-monotonic function. Okay? So typically, this can be represented by that. So if there are too much, let's say, volatile fatty acids, methanogenic bacteria cannot grow anymore, and so you don't produce methane anymore. And then typically what's happening, typically they have what they call a washout. So typically the growth does not compensate the let's say the dilution. So at some point you have no more methanogenic bacteria in the system. So this is something that people that and manage, let's say, anaerobic digester want to have to make sure to guarantee at least the stability of the system. So avoiding accumulation of volatile fatty acid, avoiding instability. Okay, so typically, okay, we assume in that case that methanization is a limiting step. Okay, so in that case we may have accumulation of volatile fatty acids, and so typically we use the slow fast, let's say, reduction that I mentioned before, by assuming that methane is a low solubility product and the acidogenesis is a fast reaction. And then this is exactly the algebraic equation that I obtained in that case. And so typically I can rewrite the dynamics of, let's say, the volatile fatty acids by using this reduction as follows. So this is the model that I can use in that case. Okay, use that I have the inlet of organic matter concentration here, and I have the methane gas flow rate here. Okay, and this is typically an example that we have in that case. So typically, if you see, where is it? Too fast. In that case, you see that the control works well for the volatile fatty acids. Okay, these are the results of a European project that it was called Amoco that I had quite a while ago. Okay, and then, okay, we can do one step further. Okay, so is it possible to get to optimal operating points without knowing what is the operating point? So once again, a lot of uncertainty about the system, but we know that so on paper we know, and we know from practice that there is an optimum somewhere. Okay, and that's really the job of adaptive extremum seeking. So you do control at the same time that you do optimization. Okay, I mean in chemical engineering people tend to call that real-time optimization. Okay, but that's simply adaptive extremum seeking. So this is adaptive control, but at the same time the adaptation is related to the fact that you are looking for the optimum in closed loop. Okay, And so there are a number of, let's say, I mean, I have a lot of results on that, but then there are typically two types of situations. One, the model structure is fully known, and one is which is partially known. I just use an example for the second part. So once again, I go back to a simple example, okay? One biomass, one substrate, and one product. So this is the equation that we have obtained by model reduction, and we assume that we have a mono equation in that case. So we don't know the parameters of the mono model in that case, and for, let's say, but this is not a strong assumption. For let's say, convergence analysis, we need to assume that this term is bounded. And we assume that we measure the gas flow rate, and we measure the substrate concentration S. So what we do, we define three new parameters, theta mu, theta S, theta K, and we write the dynamics of the system as follows. So we compute, let's say, time derivative for y, which is exactly what we have here. Note that we have this at the denominator, okay, which will be interesting to understand. So if I want to make sure that I have an optimal point, I compute, let's say, twice the derivative of y with respect to s, okay? You see this term is strictly negative, and you see that there's an optimum if this term is equal to 0, okay? So the optimum is for the concentration of substrate, which is equal to this value, okay? And so this is, so two steps. First step is the parameter estimation. Once again, this kind of, let's say, classical observer-based estimator, okay? And so the parameters are in the two equations here, and I update the parameters by using this, except that I also use a projection algorithm in that case to avoid to have a division by 0. So since I have this term here, it might happen that this term becomes negative, and so this might be equal to 0, so we use a projection algorithm to avoid, let's say, division by 0, typically. And so, let's say the control law is very looks like, you know, if I look, is let's say, kind of an extended version of the adaptive generalizing control that I mentioned before, except that I have this term, and I have a term which is d and d dot, which is called as the data signal, or let's say the excitation signal if you prefer, okay? In that case, and so this is my control error, but with the data signal also at the same time, okay? And so if I want to look at the convergence of this, I have this Lyapunov function, and so remember that I have this term somewhere at the denominator in my equation for y, okay? So this is probably one of the nice tricks in this case. So this is classical. I have a term which is the square of the control error, terms which are related to the square of the error in the parameter estimation, and then two terms which are related to the estimation of, let's say, the observer based part of the parameter estimation. Okay, and so it's easy to show that in that case I have this value for the time derivative of v. Typically, I can invoke the LaSalle-Yoshizawa theorem and the LaSalle invariance principle to show that what I have is that, you know, I will converge close enough to the optimum in that case, which is exactly the result that I have here. So typically, these terms are related to the external excitation or the data signal, if you prefer. So if this term will tend to 0, if my data signal and its time derivative will tend to 0. So in that case, I can show that I converge to the optimum without knowing the optimum. Okay, that's the idea of adaptive extremum seeking. Just a few simulation. So note that in that case, because it is a maximum, it's impossible to move up over it. Okay, we are always below it. Okay. But then this is exactly what we have, the convergence of the parameter in that case. And the fact that if we remove the data signal, it will tend exactly, so it can remain close enough to the optimum. Then if I remove the data signal, it will tend to the optimum, okay? The parameter in that case, in this case. So a lot of possible, let's say, extension of that. This is an extension for chemical reactors. Remember that I have the concentration of the different reactant products, the temperature here, and in that case, typically what we want to, we know that there is an optimum in that case, typically when I have sequence of reaction, which is the case here, A, B, and C, which is indeed the part of the what is called the Van der Waals reactor. So we start, so the optimum is somewhere here. We start from nowhere, if I may say it like this, and you see that it converges to the optimum. Okay, so I'm at the end of my presentation, so I would like to thank you very much for your attention, and I'll be happy to answer any question. And before that, I'd like to put that in your agenda. In 2 years from now, we are going to have, let's say, the ECC here in Brussels, but on the UC Louvain site in Woluwe. So thank you very much, and I'll be happy to answer any question that you may have.
So time for questions. Alejandro, I know you want to make some question.
Well, since I have the floor, thanks, Denis, for an amazing presentation. Similarly, Emanuele wants a question from my chemical viewpoint. I was wondering, when you are talking about water treatment, you mentioned digestion in this case, but when you mix processes like digestion and also with the removal of nitrates, and also phosphates, you have an interplay between two different time constants over a long process. So in that case, it's better to decouple the chemical reactions, to treat them all together, or what would you do in that case? I mean, let's say digestion depends on the amount of oxygen that you are injecting to the reactor, while the removal of nitrates and nitrates depends on the quantity of organic matter that you still have, because it's an oxic product, but you don't have a lot of oxygen, for instance.
No, but what you mentioned is another type of process,
Yeah.
Wastewater treatment. So this one is anaerobic digestion. Anaerobic digestion is exclusively used to, let's say degrade carbon, okay? And big molecules typically not nowadays. So what you mentioned is typically what is called activated sludge processes. Mm-hmm. And I know in that case, but for me this is not an issue fundamentally, because typically the people tend to organize the degradation in steps. So I mean, you have anoxic and aerobic phases when you do different things. So let's say nitrogen transformation, denitrification, nitrification, and so on. And so then in that case, this issue is still is working well, and the time constant, the fast time constant is only for oxygen, but the oxygen is not an issue because you are able to control oxygen quite well today. So with that respect, this is not an issue. Probably an issue is probably with phosphate. That's a different, that's for sure. That's phosphate. And phosphate is still difficult. Yet, the problem today with nitrogen is nitrite. Okay, so the problem is nitrites. You tend to let's say nitrite is an intermediate. You know that. I mean, you have let's say ammonium, nitrite, nitrate, and typically the problem is the intermediate. Typically, in that case, and it's not completely so. Okay, so one of the projects on which I'm working today is, let's say. It's called Mokope, and it's typically the treatment of wastewater of Paris and its suburbs. And so typically they have problems when they have what they call, let's say, extreme events like big storms and things like that. So typically in that case, it happens that they can go up over, let's say, the norms in that case. And typically nitrite typically is the issue. Okay. And on top of that, for me, the issue of let's say this municipal wastewater treatment plants is, let's say, what we call the micro, let's say, pollutants, which is something which is quite difficult to handle today. But this is another story. There's a lot to say about that.
Without neglecting the small number of measurements and instruments that you have there.
In that case, it's impossible to measure them because it's trace. It's not concentration. It's traces. But you know what trace is. So typically, concentration you can have what we call, I would say, milligram per liter. This is standard. But in that case, traces is very, very small. Let's say concentration and it's very difficult to measure. And that's a big issue today.
And that is my second question is, how would you sell to chemical engineers, to design engineers, the relevance or how important control and knowing the models is? Because usually you have many steps along the design of a chemical plant or a chemical process. Conceptual design, basic engineering, detail engineering, and at the end we end up with this P and ID instrumentation, pipes and instrumentation diagrams that they come with the closed loops, with all the instruments, but for basic control, for PIDs and perhaps on-off or something about related to optimization perhaps, as you said, RTO. But they are so rigid that you cannot modify the control policies and the control loops. So how would you sell this to the engineers designing the plant, saying that it's important to design along with how to control the plant in the future?
Okay. For me, the issue in the chemical and the biochemical industry today is the fact that you have more and more, you have no more, let's say, steady state operation. This is something that is not let's say, the case in so many applications in practice. And so the issue is to know the dynamics. And for me, it's a question of education. So first year in engineering, there should be a course of dynamical systems. So people have to understand that the fundamental is the fact that you have to understand that you have systems that are changing with time. And then the rest will follow for me. But this is a problem of education. Still today, and this is typical in chemical engineering, any reactor design course is based on steady state models. That's crazy. That's just crazy. How can you convince people from industry that control is important? Control is related to the fact that you have to deal with dynamical systems because the systems are in dynamical situation. Even when you have a disturbance, when a disturbance comes into the system, this makes the system become, in dynamic situation. And that's where it's so important. Control is so important. But the difficulty, for me, the difficulty is a question of, control. Engineers have a mind that is related to steady state, to equilibrium. But equilibrium is just a specific case, a very specific case. Maybe an objective, but it's a specific case. For me, the main issue is education.
There was a question from Michel, I've seen.
So thank you for the talk, Denis. I was wondering when you spoke about adaptive control, not the extremum seeking case, but the other one, you didn't mention anything about persistency of excitation or what sort of excitation. So where is it hidden? Is it hidden somewhere?
Maybe I should. It happens that when you have a simple controller, the notion of I didn't put. I should have. Let's say the Lyapunov function in that case. And I see, in many cases, if you end up with a very simple controller, okay, since it is nonlinear. Let's say the regressor, so which has to be the source of excitation, the regressor, is a nonlinear term, and the fact that it is different from zero is enough to guarantee, let's say, the persistence of excitation condition. in this case. And in other case, the fact that the system is changing with time, then if you have two, typically you can see that these two regressors are inherently, let's say, changing this time differently, so which guarantees the persistence of excitation. It's very specific. So in that case, it's very specific to the fact that we use the knowledge of the system in that case. And I don't hide anything. This is, yeah, it may look hidden, but it's not the
I
case.
don't claim you are hiding something, but
No,
it was
no,
just
no,
a matter
no,
of speaking.
No, but that's the main issue. I mean, that's why adaptive control failed to be, let's say, widely used in industry because of that. Because in many instances, let's say, people use linear controller and it end up with controller that do not, they cannot converge, and they have explosion of the closed loop system.
Thanks. So I'm from a completely different field, so it's interesting to see your presentation, but I'm not sure if I follow everything. But one thing that struck me is that throughout you seem to assume well mixedness of the systems that you're looking at, so that the concentrations can be described by a single variable, that is a scalar variable. In sort of my field, sometimes we've moved away from this kind of sort of like pretty equations to go more to simulations that are more individual based, because that well-mixedness assumption is violated. And I'm just curious whether that's whether you've sometimes felt the need also to move away from that.
So
that,
it's a personal
assumption.
it's a personal decision to make a presentation considering only homogeneous systems. But I worked a lot on what is called distributed parameter systems, PDEs, which are so very largely used in let's say, in reaction system, chemical engineering, for instance. It happens that I have a book that will come out, let's say, these days on that topic. So, of course, then in that case, then and I know how to handle typically. I mean, of course, it's more complex than what I've shown here.
Sure.
But of course, there are many ways to extend, let's say, what I said to cases where I don't have, I clearly don't have homogeneous condition.
And with how much of this framework then carries over to the
typically
to
the dynamical model,
case?
the general dynamical model that I mentioned before is typically the same, except that in terms of having what I call the dilution term, I will have a term which is related to diffusion and one is related to convection, typically. And then, of course, of course, this is a major source of differences, and then, you don't have the same systems either. I mean, so you don't have. But typically, for instance, my reaction invariant property applies directly to this kind of system, even if it's not homogeneous, for instance.
Great, thank you.
So that's, but I agree. It was really a personal decision to just concentrate on that. It's sufficiently complex to explain what I tried to explain.
Okay, so I would propose to thank once again Denis for the very nice presentation and the very nice discussion, and to end here the first part of of our seminar series. So let's have an applause for Denis.